Look at your hand. If you're wearing anything gold right now, a ring, a chain, a watch, you are carrying a piece of one of the most violent events in the entire universe. Because every single atom of gold on Earth was forged in the collision of two dead stars, objects so dense that 1 teaspoon of them would weigh more than 5 billion tons, heavier than a mountain. They are the size of a city, yet they hold more mass than our sun. Some of them spin 700 times every second, and they began their lives as enormous blazing giants. So how does a giant star die, shrink to the size of a town, and end up making the ring on your finger? To answer that, we're going to follow one star from the moment it runs out of fuel to the instant it forges gold. This is the life and death of a neutron star. Our star is a monster, somewhere between 8 and 20 times the mass of the sun, and for millions of years it has been locked in a tug of war. Think of a star as a constant fight between two forces. Gravity is always trying to crush it inward, and the nuclear fusion burning in its core is always pushing back out. As long as those two are balanced, the star is stable, like a balloon holding its shape against a squeezing fist. To keep pushing back, the star fuses lighter elements into heavier ones, hydrogen into helium, helium into carbon, and on, building heavier elements like the layers of an onion, until it hits iron, and iron is a dead end. Fusing iron doesn't release energy, it costs energy. So the moment the core turns to iron, the furnace shuts off, the outward push vanishes, and after a million-year standoff, gravity wins in less than 1 second. The core, about 1.5 times the mass of our sun, collapses from something the size of Earth down to the size of a city in the blink of an eye, falling inward at nearly 1/4 of the speed of light. The pressure is so extreme that atoms themselves are crushed, electrons are rammed into protons, and the whole core is squeezed into a solid ball of neutrons, and then it slams to a stop. The neutrons refuse to be packed any tighter. Imagine a crowd so tightly jammed that not one more person can fit, and the collapsing star rebounds off its own core. That rebound detonates the outer layers of the star in a supernova, an explosion so bright it can briefly outshine an entire galaxy of 100 billion stars. When the light fades, the giant is gone, and in its place sits something new, a neutron star. Our neutron star holds more than the mass of the sun, crushed into a sphere barely 20 kilometers wide. You could drive across its entire surface in about 20 minutes, but you would never survive the trip, because this object breaks almost every rule your intuition runs on. Start with its density. Remember that teaspoon. 1 teaspoon of neutron star material weighs around 5.5 billion tons. That's the weight of roughly 900 Great Pyramids of Giza balanced on a single spoon. Put it another way, it's like taking every human being alive, all 8 billion of us, and crushing us down into a single sugar cube. Now the gravity. The pull at the surface is around 2 billion times stronger than Earth's. If you dropped a marshmallow onto a neutron star, it would hit the surface with the energy of an atomic bomb. You wouldn't fall onto a neutron star so much as be smeared across it, flattened into a layer of atoms. That crushing gravity also makes it the smoothest object in nature. On Earth, mountains rise for kilometers. On a neutron star, gravity is so ruthless that the tallest possible mountain is a few millimeters high. This city-sized ball is rounder and smoother than any marble ever manufactured. And then there's the spin. When the giant core collapsed, something happened that you've seen a figure skater do. When a spinning skater pulls their arms in tight, they whip around faster. Our star did the same thing. It collapsed from something vast to something tiny, and its spin exploded. Some neutron stars rotate more than 700 times every second, their surfaces racing around at a large fraction of the speed of light, faster than the blades of a kitchen blender. Many of them do something even stranger. They fire beams of radio waves out of their magnetic poles, and as the star spins, those beams sweep across space like a lighthouse. If one of those beams happens to point at Earth, we see a pulse, ticking with the precision of an atomic clock. We call them pulsars. And here's a piece of history worth knowing. In 1967, a 24-year-old PhD student named Jocelyn Bell Burnell was combing through data when she found a signal pulsing every 1 1/3 seconds. so impossibly regular that the team half jokingly labeled it LGM-1. LGM, as in Little Green Men. For a moment, they genuinely wondered if they'd picked up a message from an alien civilization. They hadn't. They had found the first pulsar, the spinning corpse of a dead star keeping perfect time. Some neutron stars are even more extreme. We call them magnetars, and they carry the strongest magnetic fields in the known universe, 1,000 times stronger than an ordinary neutron star, and quadrillions of times stronger than Earth's. A magnetar's field is so powerful that if one sat halfway to the moon, it would wipe the data off every credit card on the planet and scramble the electrical signals in your brain. In 2004, a single starquake on a magnetar 50,000 light-years away sent a wave of energy across the galaxy that measurably disturbed Earth's upper atmosphere from 50,000 light-years away. So, a neutron star is the densest, smoothest, fastest spinning, most magnetic object in the cosmos. But we still haven't answered our opening question. How does any of this end up as gold on your finger? For that, we need two of them. Sometimes neutron stars are born in pairs, locked in orbit around each other, and for millions of years they circle, slowly, relentlessly spiraling inward like two marbles rolling around a drain. As they orbit, they shed energy in the form of ripples in the fabric of space itself, gravitational waves. Every ripple steals a little of their orbit, and they fall closer and spin faster, until finally they touch. In 2017, humanity caught this happening for the first time. Detectors on Earth felt the gravitational waves from two neutron stars colliding 130 million light-years away. And when they merged, they released a burst of light called a kilonova. In that instant, a cloud of pure neutrons was blasted into space, and in the chaos, the heaviest elements in existence were assembled: platinum, uranium, and gold. That single collision is estimated to have forged several times the mass of our entire planet in gold alone. That gold doesn't stay put. It drifts through space for billions of years, mixing into vast clouds of gas and dust. And when those clouds eventually collapse to form new stars and new planets, the gold comes along for the ride. Some of it ended up here, baked into the young Earth. Later, we dug it out of the ground, melted it, and shaped it into the ring on your hand. So the gold you wear is not really from Earth at all. It is the ash of a dead star collision that happened before the sun was even born. Neutron stars are the universe's most extreme laboratories. They let us test the laws of physics under conditions we could never recreate on Earth. But they're also something simpler than that. They're a mirror because they tell us that some of the most precious things in our lives were not born from calm or peace or gentleness. They were born from collapse and pressure and collision, from the violent death of something enormous. So the next time you catch the glint of gold on someone's hand, remember what you're really looking at: starlight that outlived the star. We are all just walking around, quietly wearing the oldest scars in the universe. I'm the onlooker. Keep looking closer.